This Zoom session is being brought to you by the Fractal Snowflake Curve. All right, where are we? Ah, there we are. Okay, for today, we start out with chapter 8, 8.1 and 8.2 about sequences, summation notation, and arithmetic sequences and summations. Okay, sequence. It's a list of numbers with a subscript, A1, A2, A3, A4, AN, and so on, and indefinitely, usually. A1 is the first term, AN is the nth term. Some of them are defined by formulas. So for example, here we have AN is 3n plus 2. So it goes 5, 8, 11, 8 is 26. It goes up and so on like that. The first term is 5, and each one differs from the previous one by 3. Here's 5 to the n, bn. So it goes 5, 25, 125, and on and on and on. Eighth term is 390, 625, and so on, rising quite rapidly to infinity. Now, these are defined by formulas, closed formulas. You just plug in a number and out comes a number. Some are defined what I call recursively. You have to start from the first, and from the first define the second, from the second define the third, and so on iteratively. Here's one. A1 equals 1. AN is 2AN minus 1 plus 1. So A1 equals 1 is the initial condition. AN equals 2AN minus 1 plus 1 is the recursion. It defines a given term from the previous term. So for example, we start with 1. For A2, we'd have twice that plus 1 is 3. For A3, we have twice 3 plus 1 is 7. For A4, we have twice 7 plus 1 is 15. For A5, we have twice that plus 1 is 31, and so on indefinitely. 1, 3, 7, 11, 1, 3, 7, 15, 31, and so on. Now, I believe you can define a closed formula for this, but it's a subtle thing. There's an exponential and subtracting a term and so on. Here's a classic one, the Fibonacci sequence. It starts off with the initial condition of A1 equals 1 and A2 equals 1. And each subsequent one is the sum of the previous two. This shows up all over the place. So 1, 1, 1 and 1 is 2, 1 and 2 is 3, 2 and 3 is 5, 3 and 5 is 8, 5 and 8 is 13, and so on, 21, 34, 55, 89, and so on indefinitely. There is a closed formula for this too. It involves the golden mean, an irrational number, which somehow is strange considering these are all integers. Okay. Here's an example. P naught is 5,000. Pn is 1,108. Pn minus 1 minus 300. This, I gather, is some kind of exponentially growing bank account with 300 being paid out each month. So here we go. It starts at 5,000. Add that by 1, multiply that by 1.08, and add 300, subtract 300, and we get 5,100. And after that is 5,200. After that is 5,324, 5,450.61, about 5,586.66. I run off at the penny level. 5,733, 59, and so on. Going on, P12 is P12 is about 6,897.71. So that's what, if this is a bank account or bank account, that's a yearly interest, and this is being how much is paid out from it, and that's what it would be on the 12th year. If we have a sequence, if we add them up, A1, A1 plus A2, A1 plus A2 plus A3, A1 plus A2 plus A3 plus A4, these are called partial sums, denoted SN, so the sum from 1 up to n. It's also denoted this way. Sigma, big letter, Greek letter sigma, k equals 1 to n of ak. This denotes the sum from A1 up to AN. This is denoted, called sigma notation on account of the Greek letter sigma. Sigma for sum. So for example, k equals 1 to 4 of k sums to what? Well, it's 1 plus 2 plus 3 plus 4 is 10. Sum from 1 up to 6 of 1 of k is what? 1 over 1 plus 1/2 plus a third plus a fourth plus a fifth plus a sixth. Punch it into a calculator, push the 2 fractions button. It says 49 out of 20. Sum from 1 up to 10 of k squared is 1 plus 4 plus 9 plus 16, 25, 36, 49, 64, 81 plus 100, 10 squared, which if you add it up is 385. Okay, that's that for that.